Hello students, welcome back to OrganiChemVerse. In the last lecture, you learned why carbon is considered as the king of organic chemistry. In this video, we will explore what hybridization is. We will also learn some easy steps to identify the hybridization of atoms within the organic molecules. So let's get started. So, what is hybridization in general? Students, you might have come across hybrid vegetables or hybrid fruits. So what exactly are these hybrid? Let's take example of a fruit called as plum cod. Plum cod is a hybrid of plum and apricot. So why this hybridization is done? So that we enhance the properties of both the fruits and get it in one fruit, which we call it as plum cod. Similarly, in chemistry, the atoms will undergo hybridization. So what is undergoing hybridization here? The atomic orbitals. Atomic orbitals. So there will be intermixing of atomic orbitals and they are going to form a brand new orbitals called as hybrid orbitals. These hybrid orbitals will have the properties of all the atomic orbitals which are undergoing intermixing. So in order to understand this better, we need to first understand what are atomic orbitals. For example, here I have written sp³ hybridization. It is a type of hybridization, right? So what exactly this means? That means there is one s orbital and look at this. There are 3 p orbitals which are undergoing intermixing and it is going to form sp³ hybrid orbital. So we write it as s1p3, but since it is only one, so you don't have to write 1 here. It is not necessary. You can write it as sp³. And students, don't make a mistake of calling this as sp³. Okay, it's wrong. You have to call it as sp³ to show that there is one s and 3 p orbitals which will mix together to form a hybrid orbitals called as sp³ hybrid orbital. Okay, let's say sp². Right? So in order to form this hybrid orbital, we have one s and 2 p orbitals, 1 and 2, right? It is going to form sp² hybrid orbital, similar to the plum cod, right? Same way for sp, there will be one s and 1 p. Therefore, it's going to form sp hybrid orbital. But what exactly are these s and p orbitals? Let's learn that right now. In order to understand hybridization, we need to know what is the structure of an atom. In an atom, the nucleus is at the center. That's where the protons and neutrons are present. And what about the electrons? The electrons are distributed into different shells. So what are these shells? These are energy levels. The shells consist of subshells and the subshells consist of atomic orbitals. Why do we have to do this? Because we need to distribute the electrons into different atomic orbitals. Then how to distribute the atomic orbitals? That can be done by writing different shells and what they are made up of. For example, if the shell number is 1, right, it is made up of a subshell as well as atomic orbital, that is 1s. And each atomic orbital can accommodate maximum of 2 electrons. Therefore, we are going to write it as 1s2. Students, remember we read it as 1s2, not 1s square, okay, and it can accommodate maximum of 2 electrons only. If there is a second shell, n is equal to 2, the second shell is made up of subshell 2s and 2p. As I told earlier, the s subshell itself is atomic orbital and it can accommodate only 2 electrons like this. What about the 2p? The 2p subshell is in turn made up of 3 atomic orbitals, that is 2px, 2py and 2pz like this. Each orbital can accommodate 2 electrons. So what does that mean? The p orbital right here put together, it can accommodate 6 electrons. Like this, for each and every shell we need to know how many subshells are there and how many atomic orbitals are there. Now for carbon, how to write the different atomic orbitals? For that, first you need to know what is the atomic number of carbon, that is 6. That means what? There are 6 electrons in the carbon atom. Now we need to distribute these 6 electrons into different atomic orbitals. Why so? Because we know that hybridization is mixing of the atomic orbitals. Will all atomic orbitals undergo hybridization? No. Only the valence shell atomic orbitals will undergo hybridization. So which is the valence shell in carbon? We don't know. So let's write that now. We can write electronic configuration for carbon by using the different atomic orbitals. What does that mean? Electronic configuration means distribution of electrons into different atomic orbitals. The electrons first will go to the lowest energy state. Therefore, the first 2 electrons will go to the 1s orbital. So it will become 1s2. How many electrons are left over now? 4 electrons. So where the next electrons will go to? 2s atomic orbital. So that is 2s2. How many left now? 2 more electrons. So where it will go to? The 2p orbital, like 2p2. Right? We have distributed the electrons. Now we need to identify the valence shell. Which is the valence shell? Valence shell is the outermost shell. Outermost shell. That means what? Only the second shell will take part in the mixing of atomic orbitals to form hybrid orbitals. In order to understand this mixing of atomic orbitals, we need to know what is the shape of s orbital, what is the shape of all these p orbitals, and also I have written px, py, pz. What exactly are these x, y, z? So let's learn it now. Students, remember the hybridization is mixing of atomic orbitals of the valence shell. So for carbon, the valence shell is 2 and this shell is made up of the subshell 2s, which is also an atomic orbital 2s. Then what is the shape of this s orbital? It is spherical in shape. That means if this is a nucleus, the probability of finding electron around this nucleus is in the spherical shape. This is where the probability of finding electron is maximum. And what is the shape? It is spherical. Let's take for the 2p subshell. The 2p subshell is made up of 2px, 2py and 2pz orbital. Then what are these x, y and z? Let's take axis x. The p orbitals are dumbbell in shape like this. There are 2 lobes, right, where the probability of finding electron will be maximum. Since the p orbital is aligning on the x-axis, we call this as px and it belongs to the second shell. That's why we call it as 2px. For 2py, say if this is x orbital and this is y orbital, the p y orbital will be aligning on the y axis. and the probability of finding electron will be on this axis, right? For Z, I think by now you might have guessed it, right? If this is X and this is Y, this is Z, the orbital will be aligning on the Z axis like this. So the probability of finding electron in this space is in dumbbell shape. And what do you call this as? This is 2pz. So 2px, 2py and 2pz. By now you know what this x, y and z refers to. So once you know the shapes of the orbitals, now you will know what will be the shape of the hybrid orbitals. Let's learn that. Students, now that you have learned what are shells, subshells and atomic orbitals and their shapes, it's time to learn the hybridization. First, let's understand what is sp³ hybridization. Whenever we learn hybridization, we always do it by taking an example. For sp³, let me take example of methane. In methane, carbon is the central atom which will undergo hybridization. So for carbon, let me write down the atomic number, that is 6. That means there are 6 electrons. So we'll distribute all the electrons so that we will know what is the valence shell. This is the valence shell because only the valence shell will participate in the hybridization. In order to distribute the electrons, let me write the orbitals as box, right? If this is 2s, this will be 2p subshell. And how many electrons are there in 2s? There are 2 electrons. In 2p also there are 2 electrons. This is the electronic configuration of carbon in the ground state. When the carbon is approached by the hydrogen atoms, it undergoes excitation. That means the electron will jump from 2s to 2p. So how do we show that now? You see the 2s will have 1 electron and 2p will have, each orbital will have 1 electron like this. Now, before we start mixing the atomic orbital, let's check how many atoms are approaching carbon. There are 4 hydrogen atoms approaching carbon. That means the carbon must be ready with 4 hybrid orbitals. Students, note that the number of atomic orbitals mixing will be always equal to the number of hybrid orbitals. So in order to form 4 hybrid orbitals, 4 atomic orbitals should mix now. What are the 4 atomic orbitals we have now? You see, there is 1 s orbital and there are 3 p orbitals. Therefore, how many are we going to get? We are going to get 4 hybrid orbitals. But what sort of hybrid orbital? s1 p3. That means sp3 hybrid orbitals. Now that we got 4 sp3 hybrid orbitals, let's see what will be the shape of these hybrid orbitals. The s orbital, we know it is spherical in shape. What about the px? It is dumbbell. Say this is px. Py is also dumbbell, but it is on the y-axis. And this is pz. It is on the z-axis. All these atomic orbitals will undergo intermixing or mixing to form hybrid orbitals of shape of both spherical and dumbbell. What exactly it means? In case of a hybrid fruit, as I was telling you earlier, plum cod, it had properties of both plum and apricot, right? Like that. The S is spherical in shape, right? What about the P? The P is dumbbell, similar to that. But the difference is in dumbbell, one lobe is of larger size, the other lobe is smaller size. That means what? The probability of finding electron in the larger lobe will be greater. That means only that lobe will participate in the overlapping of the orbitals. Here I have written only one sp3 hybrid orbital. Since there are 4 atomic orbitals, we know it should form 4 hybrid orbitals. So let's write down 4 hybrid orbitals. All these hybrid orbitals will stay as far as possible from each other due to repulsion of electron cloud, like this. Okay, so we got 4 hybrid orbitals of sp3. Now it is ready to overlap with the hydrogen. So each of them will have 1 electron. So they will share their electrons with the incoming hydrogen atom. So if this is hydrogen atom, it shares its electron. Sharing of electron will lead to formation of a covalent bond. The covalent bond here, it is called as sigma bond. Why sigma bond? Because the orbitals are undergoing head-on overlapping. So you see there will be one more hydrogen atom which will undergo overlapping. We got one more. What about here? There is one more hydrogen atom, sigma bond. Same here also, hydrogen sigma bond. What sort of overlapping is taking place here? sp3. Here also sp3. So due to sp3 overlapping, we are getting 4 bonds. So how to write the methane molecule now? All the hydrogen, if they stay as far as possible, right, in a 3-dimensional space, then it will have the shape of a tetrahedron. So that's why we call the shape as tetrahedral shape. And what will be the bond angle here? The bond angle will be 109 degree 28 minutes or 109.5 degree. So why hybridization is important? Because it helps us to know the geometry of the molecule, the shape of the molecule and the bond angles in the molecule. Now let's do the sp2 hybridization for ethene molecule. Students, now let's learn sp2 hybridization. For sp2 hybridization, let's take example of an organic molecule, ethene. What is the molecular formula of ethene? C₂H₄, where the 2 carbons are attached to each other by a double bond and the hydrogen atoms are attached to carbons as shown here, like this. And both the carbons here are sp2 hybridized. So how to show sp2 hybridization for carbon? As usual, we write carbon, the atomic number is 6. Its electronic configuration is 1s2, 2s2, 2p2, right? The inner shell will not participate in the hybridization, only the valence shell. So let's write down its electrons in the ground state. You see the 2s will have 2 electrons and the 2p will also have 2 electrons. This is in the ground state. When the carbon is approached by the other atoms, it will undergo excitation and you see each orbital is having 1 electron like this. And what do you call this? Excited state. Since the carbon is approached by 3 atoms, since there are 3 atoms, we have to form 3 hybrid orbitals. When 3 hybrid orbitals will be there, 3 atomic orbitals must undergo mixing. What are the 3 atomic orbitals we will mix here? 1s and 2p. So how do you write that? 1s and 2p orbitals will mix to form 3. What sort? See here, S1P2, that means sp2. 3 sp2 hybrid orbitals will be formed. So how do you write the shapes of these atomic orbitals and the hybrid orbitals? So let's do that as well. So we have s orbital, which is spherical in shape, right? We have a 2p orbital and one more 2p orbital like this. So since 3 of them are mixing, we have to write 3 hybrid orbitals. So how do we write hybrid orbitals here? It should be mix of all these. So a larger low and a smaller loop, larger loop, smaller loop, larger loop, and smaller loop. And they stay as far as possible from each other. So this is for one carbon, right? Since they are hybrid orbitals, we can write like this also, okay? Similarly, there is one more carbon which will undergo intermixing, and it will also form like this, okay? So here you see that it will, all of them will have one electron each, like this. Now, what about the fourth electron? The fourth electron, whatever is present here, it is present in unhybrid. Unhybridized means what? It's the normal p orbital. That means what? It will be like this. There is one electron here, the other electron is here, like this. Now, both the carbons will align in such a way that there will be a bond formation between these two. So how to align them in the proper geometry or the proper axis? So let's see that. The carbon and the other carbon should undergo overlapping. So this is one hybrid orbital, this is the other hybrid orbital. What do they do here? They share their electron, therefore they are going to form a sigma bond. What about the other hybrid orbitals here? There is one hybrid orbital, the other hybrid orbital. Students, remember all these hybrid orbitals will be of same size and same shape. While I am drawing, there might be some mismatch, but remember they will all have same size and shape. Okay. So these are the three hybrid orbitals. What about here? It will have one electron here, the other electron here. Just you observe this carbon. It already formed bond over here. What about this one? It is forming bond with the other hydrogen atom like this. And what is this? This is a sigma bond. What about the other hydrogen atom? This is also sigma bond. What sort of overlapping is taking place? sp², sp². What about here? sp², sp², head-on overlapping. Now, let's do the same thing for this molecule also. I mean, this for carbon also. See here, right? It's in the same molecule only, right? So you have to say atom. So here, again, the hydrogen will share its electron. Here also the hydrogen will share its electron. Again, we got two sigma bonds. Students, what we have not accounted so far for the unhybrid orbital. Where is the unhybrid orbital? Here. Okay, like this. And it also has one electron. Now what happens is this unhybrid orbital, they are parallel to each other and they share the electrons like this. This is also called as lateral overlapping, and due to this lateral overlapping, we call this as a pi bond. This is a weak bond as compared to the sigma bond, because in sigma there is a head-on overlapping. Here it is a sideways overlapping. So how do you write the molecule now? Like this. There is sigma, there is a pi, and now between carbon and hydrogen there will be always sigma because there is a head-on overlapping like this. And what will be the shape of the molecule? Just look at this. It will be trigonal planar because the bond angle here it will be 120 degree and it's a planar structure. So sp² hybridization is helping us to know the bond angle and what will be the shape of the molecule. Let's learn what is sp hybridization now. Ethine is an organic molecule with sp hybridized carbons. So let's understand sp hybridization in detail by using ethine as an example. Both the carbons are attached by a triple bond in ethine and both are sp hybridized. First, we write the electronic configuration for carbon as usual. Now you see we don't use the inner shell. Let's use only the valence shell and do the electronic distribution in the ground state. 2s will have 2 electrons and 2p will have 2 electrons. As the carbon is approached by the other atoms, it will undergo excitation. You see, each p orbital will have 1 electron. By now, we know that when the atom is approached by 2 atoms, it should be ready with 2 hybrid orbitals. So that means what? 2 atomic orbitals should undergo mixing. What are the atomic orbitals undergoing mixing here? 1s and 1p. So 1s and 1p will mix to form 1 plus 1 is 2. And what sort of hybrid orbital? sp. 2 sp hybrid orbitals will be formed. How do we show it with respect to the shapes of the atomic orbitals? If this is the s orbital, right, and the p orbital is dumbbell like this. In fact, it is 2s and 2p. You can show like this also, okay? It's going to form 2 hybrid orbitals like this, right? One larger lobe, one smaller lobe. Only the larger lobe will take part in the bond formation. There will be one more hybrid orbital, right? They stay as far as possible from each other. So we got 2 hybrid orbitals like this. Students, remember the hybrid orbitals, both of them have 1 electron each, and they are trying to stay as far as possible from each other, and they will have same size and shape also, right? So this is for one carbon. Similarly, there is one more carbon which is ready with the sp hybridized orbital. So now they should undergo overlapping. What about the p orbitals? They are unhybrid orbitals, or they are just normal p orbitals. They're as it is. Okay. So now let's show for both the carbons. So there is a carbon here. It is having 2 hybrid orbitals like this. You see, both of them have 2 electrons like this. Okay. So this is where the probability of finding electron is maximum. So we have one more carbon, right, that also has a hybrid orbital here and here like this, right? You see, both of them will have 1 electron each. So when these two overlap, that means what? They share 2 electrons. By sharing 2 electrons, it's going to form a covalent bond, and it is head-on overlapping. Therefore, it is a sigma bond. What about here? You see, it is overlapping with the hydrogen atom like this, and it shares electron. So what is the overlapping here? S and sp, and it is head on, therefore sigma. Similarly, we have one more hydrogen atom here, and it is also undergoing head on overlapping, so sigma, and the overlapping type is ssp. What about here? sp and sp. Now, so far we have not accounted for the unhybrid orbital electrons. Say, let's assume if this is happening on the x-axis, okay, then what about the y-axis? P orbital, it will be as it is. So this is also py, this is also py. So they are parallel to each other, and both of them have electrons like this. Since they are parallel to each other, they undergo lateral overlapping. The lateral overlapping will form a pi bond. So I have accounted for a py orbital, right? What about the pz? So that will be, say, like this. You see, this also will have 1 electron like this. Then what happens? It will undergo sideways like this. The sideways will always give you a pi bond. That means what? Whenever 2 atoms form multiple bonds, that means 2 bonds, 3 bonds, etc. The first thing they will form is a sigma bond. Then it is going to form pi bonds. The next whatever bonds are there, they are pi bonds. And what about here? Sigma bonds, because that is the first bond, right? So between hydrogen and any other atom, it's sigma bond. Now look at this, all of them are in the same line. That means what? It is linear in shape. And what about the bond angle here? You see, it is 180 degree. That's why in sp hybridization, the carbon is linear in shape and the bond angle is 180 degree. The sp hybridized carbon will always have two pi bonds. That is always formed by the lateral overlapping of the unhybridized atomic orbitals. This is what very important when it comes to sp hybridization. You don't have to do all this to find out the hybridization of atoms in a molecule. I'm going to give you a simple trick to find the hybridization of atoms in molecules. So let's do that now. Students, you have learned in the previous lecture that carbon can form many organic molecules. I have written some of the organic molecules here. Let's find out what is the hybridization of carbon atoms in the given molecules. For this, you have to follow the simple rule. What is the rule? If a carbon is attached to 4 sigma bonds, then it is sp3 hybridized. Say, for example, in this molecule, you see there is no double bond or triple bond. That means what? All of them are sigma bonds. Therefore, here it is sp3 hybridized. Here also 1, 2, 3, 4. So, sp3 hybridized, sp3 hybridized. If all the carbons are sp3 hybridized, we call such molecules as alkanes. In fact, the given molecule is propane as it has 3 carbons in it. Let's analyze the second molecule. You see there is a double bond. In that case, if there are 3 sigma bonds, then it is sp2 hybridized. What does that mean? Look at this. Whenever we have a double bond, I told you that there is one sigma, the other one is pi. So around this carbon, we have 3 sigma bonds. 3 sigma bonds means this carbon is sp2 hybridized. Same with this carbon also. 1, 2, 3. 3 sigma bonds means it is sp2. What about this carbon? It is attached to 4 sigma bonds. Hence it is sp3 hybridized. 4 sigma bonds. Hence it is sp3 hybridized. A molecule can have sp2 as well as sp3 hybridized carbons like in this case. Let's analyze the next molecule. It is attached to other atom than carbon. So it's oxygen. Still you can do the hybridization. How? Same rule. Count the number of sigma bond. There are 2 bonds here. That means one will be sigma. Here also 2 sigma bond. 1, 2, 3. That means what? This is a sp2 hybridized carbon. Okay. Now let's check for the next molecule. You see 1, 2, 3, 4. That means it is sp3 hybridized. The carbon is attached to nitrogen. No problem. Apply the same rule. Okay. But if there are 2 sigma bonds, then it is going to be sp hybridized. Whenever we have 3 bonds, that means it's a triple bond, then only one sigma will be there. The other 2 will be pi because they are formed from the unhybridized p orbitals, right? That's why those 2 will undergo sideways overlapping to form a pi bond. So between 2 atoms, always there is only one sigma bond. So there is only one. What about here? One more. So 1 plus 1, 2 means the carbon here, it is sp hybridized. Okay, let's take the last molecule. This is interesting, okay, because many students assume that the moment there is a double bond, it is sp2. It's not like that, okay. We have to always apply this. Okay, carbon is attached to 1, 2, 3. 3 sigma bond means sp2. What about this carbon? Both the sides there are double bonds. In that case, see, there is one sigma bond here, there is one sigma bond here. The other 2 are pi. Count the number of sigma bonds. 2 means what? This carbon is sp hybridized. Just because there is a double bond, don't think it is sp². It is sp hybridized. What about this carbon? 1, 2, 3. That means what? It is also sp² hybridized carbon. So this is how you have to check the hybridization of carbons in the organic molecules. I hope I made the hybridization concept clear to you. If you still have any doubts, you can comment them in the comment section. In the next video, I'm going to explain how to write organic molecules in different ways. Thank you for watching this video. Until next time.